Hey, what's up, Chem Peeps? One more vid here to practice intermolecular forces. We're going to look at two common ways that we can tell the relative strength of intermolecular forces. One of those ways is vapor pressure. If you put a liquid in a container and seal the container, some of that liquid is going to turn into the vapor phase. If most of the molecules stay in the liquid phase and very few turn into the vapor phase, then the vapor pressure is going to be very low, because there's not going to be a whole lot of gas molecules or vapor phase molecules banging around into the sides of the container. Recall that low vapor pressures indicate strong intermolecular forces. If the forces between these molecules is really strong, they're going to stay stuck together in the liquid phase. Conversely, if there's a lot of the liquid that heads to the vapor phase, with a high vapor pressure, or with a lot of the sample turning into the vapor phase, it indicates that the intermolecular forces are very weak. That in the liquid phase, they can't hold on to one another very strongly and quickly jump into the vapor phase. So high vapor pressures indicate weak intermolecular forces. And the second common way to determine the relative strength of the intermolecular forces is to look at the boiling points. If the boiling point is really low, just going to add a little bit of heat here. Boop. Flame. Fire. Ignite. If the boiling point is fairly low, if this boils at a low temperature, that indicates that the intermolecular forces are relatively weak. So at low temperatures, they're going to overcome the attractions in the liquid phase and turn into the vapor phase. However, if we've got a high boiling point, fire, flame, if you have to get this sucker really hot before it starts to boil, before it starts to turn into the gas phase, it means that the intermolecular forces are really strong. They're hanging on to one another with really strong intermolecular forces. So you have to get it really hot before we begin to boil and turn into the gas phase. So let's take a look at some examples. Let's take a look at dichloromethane and carbon tetrachloride. We're provided with the vapor pressures for each of these substances. Notice that the vapor pressure for dichloromethane is higher than the vapor pressure for carbon tetrachloride. This indicates that at 20 degrees Celsius, there's a lot more dichloromethane in the vapor phase than carbon tetrachloride. And if there's more dichloromethane in the vapor phase, that indicates that the intermolecular forces between the dichloromethane molecules are relatively weak, and that the stronger intermolecular forces must be between molecules of carbon tetrachloride. Carbon tetrachloride has stronger intermolecular forces due to its lower vapor pressure. Next example, we've got some benzene and some toluene. Oh, some fun cancer-causing organic compounds. Once again, we're provided with their vapor pressures at 20 degrees Celsius. Notice the vapor pressure of benzene is 75 torr, while that of toluene is 22 torr. Again, the higher vapor pressure indicates more of the substance is in the vapor phase, which means the strength of the intermolecular forces is not super great because they're easily slipping away into the gas phase. And therefore, toluene has the stronger intermolecular forces. Toluene has stronger intermolecular forces due to lower vapor pressure. Boom. Next, we've got some liquid propene and liquid vinyl chloride. Notice this time our focus is on boiling point at 1 atmosphere pressure. Here, the liquid vinyl chloride has a higher boiling point than the liquid propene. We have to get it hotter before it starts to go from the liquid phase to the gas phase, indicating that liquid vinyl chloride has much stronger intermolecular forces. It doesn't want to let go, it's going to stay in the liquid phase. Vinyl chloride has stronger intermolecular forces indicated by its higher boiling point. Final example, we've got some N2H4 and some C2H6. Once again, we're provided with the boiling points at 1 atmosphere pressure. N2H4 has a much higher boiling point than C2H6, once again indicating that the intermolecular forces between molecules of N2H4 are much stronger than those in between molecules of C2H6. N2H4 has stronger intermolecular forces indicated by its higher boiling point. Boom. Done.